discuss stack in detail. Now, queue, as you know, I mean, all of you have experience of standing in a queue in your lifetime several times. I mean, and analogically, the same concept is here used to come up with an ADT uh, and further implementation of possible data structures. So queue is basically unlike stack, uh, as you have seen, queue has two ends. One end is formally called front and other end is formally called as rear. And insertion or deletion takes place in these two separate ends, through these two separate ends basically. In stack, we have seen one end was used to insert and delete items, but here we have two different designated ends for insertion and deletion. And formally, insertion and deletions are termed as NQ and DQ operation in queue. Okay, just like push and pop that were the formal insertion and deletion operations in for stack. And again, since there are two ends, and as you have seen in queue, what happens if you want to be a part of a queue, you have to stand at the end. That means you have objects are inserted through rear end, and when uh, the service, you have to serve items one by one, that service end is basically the front end. So the the oldest element that is right now at the front of the queue will be served first. So unlike LIFO, queue implements FIFO principle, like first in first out, very fair kind of um, serving, where the first person who have entered into the queue will always get the service first. Okay, so this is basically, this analogy is very clear. I think there is nothing much problem, because all of you have acquainted with this queue concept already from our everyday life. Okay, now if you talk about abstract data type, we know that abstract data type is nothing but a template kind of thing, which just say about the possible interfaces through which this collection of object will interact with the external world. The interfaces are sometimes called the functions or uh, what I can methods like that. Okay, and every entity has some very uh, important and mandatory functions and some auxiliary functions. Just like in case of stack, maybe the important or mandatory uh, methods or functions were push, pop, and top. Now here in queue we have three um, mandatory operations or very important operations, like NQ, DQ, and front. NQ is basically, as I have already mentioned, is the synonym for insertion of an object. So NQ operation will always take the, I mean, this Q here, this S should be replaced by Q. This is a Q entity, and there will be an element to be supplied, which will be inserted, and it will return a modified queue. So that is also an additive queue. Similarly, DQ operation will only take the additive queue as its argument, because there is no need to mention the element, because always the current front element will be removed or dequeued. So you don't need to mention the element. It is by just like in case of stack, the top element, here the front element. And obviously after dequeuing, the modified ADTQ will be returned. Now another mandatory or important method will call the front, that will return, it is just to read the front element without removing it. So DQ operations will basically remove the element, that means it is going to update the queue, but front operation will not going to update the queue. It will just read the value of the current front element and return and copy that value in some variable and return it back to the user. Okay. So this is the difference between DQ and front. Front is for reading and DQ is for updating. Okay. Now there are certain auxiliary functions you can think of about queue. There are many. These may be some popular auxiliary functions which are also implemented while implementing QADT. One is new. Obviously, it has some implementation keeps one constructor function to construct an empty queue. Okay. Similarly, size may be another function which will return the size of the current queue. That means number of elements present in the in the queue. Okay. And there may be use auxiliary function called isEmpty to check whether a queue is empty or not. Because as you have seen in case of stack, also when you are trying to popping out or removing an element, you have to check whether the stack were empty or not. Similarly, in case of queue also, while dequeuing, you need to check whether the queue is already empty or not, because the dequeue operation or pop operations or any kind of deletion operations will not be defined on an empty queue. You have to check it, uh, unless your dequeue operations uh, will produce some error. Okay. So inside the dequeue operation, either you hard code is empty conditions, or you can make a separate function is empty, uh, so that that can be used in dequeue operations or sometimes outside of the dequeue function for some specific need. Okay. There may be several other auxiliary functions. I am not going to discuss that. Auxiliary list of auxiliary functions may be very large, depending on the different implementations also. Now, these uh, functions is one point, and in order to define an ADT, we need to have some axioms, as Mamata ma'am has already explained. So the axioms are basically to guide the implementation of that ADT, that what you should do, or what operations are basically allowed on the implementation and what are not, based on this template definition. So some of the axioms for queue may be like, when you create an empty queue and then you insert or enqueue one element called v, then if you try to get the front element, it should return v, because that is the on an empty queue you have inserted or enqueued only one element, that is the front element. Now if you apply front function on that particular queue at that stage, it should return the front element that is currently available, that is nothing but v. Similarly, if you just after creation of an empty queue and then insertion of an element v, and then you apply dequeue operation, it will again return to the empty queue. Okay. So these are the some of the examples of axiom. Axioms may not be this very specific stringent rule. So this type of thing actually elaborates that what are the meaning or semantics of that operations which you want to implement while implementing the ADT, the important functions like DQ, NQ, front, like that stuff. So what are allowed and what are not. So you can define lots of such example of axioms. Okay, these three basically this set of uh, primitive operations or important operations and set of auxiliary operations and axioms together gives us an idea or template of an ADT. Now, based on that, we implement, because these are the basically our guideline how to implement this particular ADT into a real data structure. So ADT is not a real kind of thing; it is a virtual. It's like like a template. Now, obeying that template, we need to implement. And as you have already seen that a particular ADT might have several implementations. Okay. So here similarly QADT may have several implementations. Okay. And first and foremost, as usual, we will, because we are very much comfortable with array, so we'll start uh, by trying an implementation using array. So let's see how QADT can be implemented into a Q data structure using array. Okay. Uh, right now, am I audible and everything is visible to you?
Yes, sir.
Yes, sir.
Okay. Okay. So in order to implement, what we'll take, we'll consider an array of sufficient size. Say size is determined by capital N, and with that array we can implement a queue. Ideally, see, based on our common sense or everyday life experience, queue should be, uh, I mean, should have an infinite length. I mean, as long as it can grow. But since we are trying to implement using array in order to get the advantages of array, the random access and simplicity, everything. So here we need to make a compromise that we cannot have an infinitely length array. So that's why sometimes some implementation of a specific entity may add up some additional constraints which were not mentioned in ADT definition. Let's see. In ADT definition, it was never mentioned that uh, there should be each full kind of operations, because see, each empty is okay, I mean that is always needed, because any deletion operations for any kind of ADT implementation, there must be a check whether the container is already empty or not. But this full thing, this needs to be added here when we are trying to implement queue using array. So that is one limitation. Okay, but since we are okay with that, because we are getting many other advantages using array, because first of all, it's simplicity, simple to code the other functions, and obviously it's random access, so it will be fast. Okay. Anyway, so in array implementation, we need to keep in mind that we cannot have an infinitely large uh, queue. So there will be some limitation. So based on the application, we need to choose a sufficiently large size of array so that we can accommodate as long queue as possible. Because using a array of size capital N, we can never have a queue which is having size more than n. It will always be less than. So anytime q can grow up to n, not more than that. Okay, so we will have an array q that will be used as the base container for q, and there will be two other integer variable we need to take, which will actually indicate the index of the current front element and current rear element. Let's say they are mentioned as f and r as shown in the figure. So anytime a portion of this underlying array will be occupied by the real objects that are part of the queue, remaining these cells, these white cells, are basically not part of that queue. Right now, for this example, the queue is starting from index 2 up to this index n minus 3. Okay, and these indices 0, 1, n minus 2, n minus 1, these places are not vacant, because you cannot make an array cell vacant anytime. It will contain garbage values. Basically, these are uh, these are out of the purview of this current queue. So its queue start from here, from this index pointed out by f, and it ends here, the index pointed out by r. So what I need for an array implementation, I need an array of sufficient size and two integer variable f and r respectively to represent index of the front element and current rear element. And based on the dynamic changes that may occur in this queue, like suppose I perform an DQ operation. That means this particular cell, this content of cell 2, array cell 2 will be removed. That means now it will go out of the queue, and the third index will be now current front. So F will be updated to point to 3 instead of 2. Similarly, if I insert or enqueue some new element, it will always be inserted at this end at n minus 2 index. And accordingly, after that enqueuing operation is done, R should be updated to hold the value of n minus 2 instead of n minus 3. Okay, so in this way, I need to build up the functions NQ and DQ operations so that this can happen. Okay, let us see how to write these functions. So this is very easy. These are the template for algorithmic definition of the functions NQ and DQ. As you have seen in NQ operation, uh, see, by default the ADTQ will always be an argument. So I have not specified that. The O is basically specifying the element to be inserted or enqueued. Okay. For DQ there will be no argument because by default Q is, or this array is already an argument, but there is no need to specify any element because we know the always the front element will be DQ. Now it is very pretty simple. First I have to check for NQ operation. See, this is an added constraint that comes for this array implementation. Since array has a finite limit, because normally if you consider the q ADT definition, there is no need to consider this full condition. I should be able to enqueue as long as I have members to be added, because infinitely long. But here, since array is having is I mean maximum size of capital N, so if already n number of objects are there in the array, so I cannot enqueue further. So that's why this condition has to be added. If full, then print error. Else, what I have to do? I have to first, since this R is pointing to the last element, I cannot override. First, I have to increment R to R plus 1. Okay. And then I will insert the new element O to that position. And obviously, now R will point to the new location, the actual real element. Okay, very pretty simple. Okay. Similarly, in DQ, what I have to do? Since the front element has to be DQ'd, see, this return statement, you should not get confused with the return statement we are usually uh, familiar in C programming, because after return nothing can happen. Okay, this return maybe consider, see, it will be actually for programming implementation, you have to copy this data QF into a temporary variable and then return after this line. Okay, remember that thing. Here this return is not the return statement of any programming language. Then this will never going to execute. Okay, since this is a pseudocode, I have the liberty of using this return like this, but in a program you should never use like this. You should copy the value of qf into a temporary variable, then update the value of f, then return that value of that temporary variable to return q. Understood? Is it okay? Hello?
Yes, sir.
Is it okay? I mean, don't get confused with
Yes,
this
sir.
position of this return statement here, okay?
Yes, sir.
Just this is for pseudocode. I have the liberty of using this. Huh? Anyway, for DQ operation, what I have to do? I have to update f. I have to increment f. That's why I am doing. But before updating, I have to return the value because I need the value of current f. So if I update f first, then I will be returning a different second front, I mean element, the next to front element actually. So remember this sequence of these operations. In case of NQ, I have to update the rear index, and that updation should take place first and then insertion in the queue. Here, the getting the value of the front element should take place first, then updation of front index should be met. This sequence is important. And initially, what will be the value of f and r? Obviously, f will be equal to initialize to 0 and r should be initialized to -1, because unless there is a single element, r it should not be f equal to 0 and r equal to 0, because f equal to 0 and r equal to 0 will mean that there is at least one element. Because what we are doing, we are what is the definition of f and r? F will always represent the index of the front element and r will be representing the index of the rear element. So when there is no rear element, r should not be equal to 0. So that's why initial values for f and r will be f equal to 0 and r equal to -1. Once a single element is inserted, it will be f equal to 0, r equal to 0. Okay. So in order to make that distinctions, we have used this. Is it okay? Only thing, still we need to figure out that what should be this full and empty. I cannot write full and empty only. I have to express this full condition and empty condition in terms of this R and F, obviously. Okay. So that is left. So do you have any suggestion? What should be the full expression for full condition and what should be the expression for empty condition? Any suggestion?
Sir, R is equal to n minus 1 is the condition for full.
Okay. And for empty?
F is greater
Zero.
than R.
Hmm?
F is greater than R.
F is greater than R.
F is greater than. Very good. Okay. So that's what you are trying to say. R equal to n minus 1 is going to replace the full and F greater than R. Okay. Pretty simple. But there is some catch in that. I mean, it's a very pretty simple array implementation, but it has some drawback. Let's see what are that. Okay. Well, pretty simple, but it has some drawback and some ambiguities. Let us see to identify. Okay. So this is our definition altogether. Let's take an example. So suppose we start with an empty queue. So this is uh, the initial state of the array. Say we are implementing the queue on a very hypothetical small array of size only 6. Okay, capital N is 6 right here. So initially r is pointing to -1, f is pointing to 0 and nothing is there in the queue. So all cells are now holding garbage values. Okay. Now let's say we are inserting the first element NQ using NQ operations. Then what will be the situation? Both F and R will now point to 0 index, and this first cell will be occupied by a real object. That means now my Q is represented by this portion of the array only. The remaining array is out of the purview of this Q. Okay. Now let us insert few more items. Let's say we insert four more items, like one by one, using calling NQ operations 4 times. Then situation will be like this. F will still point to index 0, but now R will be pointing to index 4, and now my Q is uh, representing, I mean, it starts from index 0, ends at index 4. Only this cell is out of the queue right now. Now, obviously, if I NQ one more element, then the array will be full and this condition will be satisfied. So, fine. See, R will be always n minus 1. Here n is 6, n minus 1 is 5. You take any size of array, if this type of condition occurs, I will always going to point r n minus 1, capital N minus 1. So this is done. Okay. But let us go back to this. I mean, then go in a different direction. Okay, let's see. Suppose now I am dequeuing some element. These three element I have dequeued by calling dequeue 3 times. Then situation will be like this. Now f will be updated, and after this 3 dequeue operation, f will now point to index 3 and r will point as usual to index 4. Now let's say I enqueue again one element, and that will be enqueued here. Okay, now see, this is my queue. The queue starts at index 3 and ends at index 5 right now, and these 3 cells of the array is vacant from the perspective of queue. Though they are not vacant, they are holding garbage values, but they can be used. They are now remaining unused, and still this condition is getting satisfied, this full condition. So what is happening? Ideally it is not full, still there are some spaces, but I cannot utilize. Okay, once a occupied space in the front positions and second front and third front positions have been removed, I cannot reuse them. This is the biggest drawback of this particular simple implementation. Understood? You may say that okay, we'll push them to our left side shifting. So that for that we need to update this implementation of NQ and DQ operations, and obviously those will be costly in terms of both the coding and time. Okay, but in the present scenario, this was a very simple and very clean definitions, but it is having a drawback that I cannot NQ even if the underlying array is having some space. So this is one drawback. There is another drawback. Let's see. Suppose after this I dequeue everything. Okay, one by one. Then I end up with this. Now see, after doing this, R will now point to index 5, that is n minus 1, and F will point to capital N or 6. Now see, this is actually an empty. In reality, it is an empty queue. But here, what is happening? Both the conditions of empty and full are being satisfied because it is F greater than R. So it is empty. Similarly, R is also equal to n minus 1. Both the conditions are getting satisfied in this scenario. So it's the ambiguity. Say a queue cannot be full and empty simultaneously. Can it? Okay. So this simple implementation has these two biggest drawback for which we cannot use this. So in order to summarize that, so any implementation we must be able to insert an element when there is blank spaces in the array. Okay, otherwise it will be totally wastage of, I mean, I have inserted, make it full, and then one by one I have dequeued. I have arranging some space. Why I am dequeuing? I am arranging some space, but I cannot use. So that is useless totally. Okay, and there should not be any ambiguity between full and empty. Full and empty conditions should be exclusive. It is empty. It cannot be full. Uh, okay. So in order to address this issue, what we can think of that once we have reached at the end of this, if there is some vacant space in the front or left portion of the array, it would have been better if we can go back to that position and insert there. That means logically, if we can consider this linear array to be circular, then this particular first point would have been solved. Unless we can do that, we won't be able to insert an element even if there are blank spaces in the array. Understood? So this type of configuration, if we can update our definition of this NQ and DQ in such a way that in an array we can allow this type of thing, that when I have reached at the end after NQ operations and some DQ operations have arranged some space in front side or left side of the array, if we can use that. So after reaching at n minus 1, if I can insert the item to 0th index, then 1, then 2, in this way if I can grow and I can utilize the best out of the array, then it will be very good, and it will address this particular issue. Okay, and this is what called wrapped around configuration, or popularly a circular queue. So the circular queue is basically, the circular structure is logical. Actually, it is implemented